Have you ever tried to understand something that is constantly changing, like the complex, dynamic patterns of brain activity? It is a real challenge, is it not? Time domain analysis is limited for non-stationary data because it fundamentally assumes the statistical properties of a signal remains constant over time. For signals that are continuously evolving, such as brainwaves during different cognitive tasks, this core assumption breaks down, rendering traditional measurements unreliable and potentially misleading. Think about it this way. A stationary signal has a mean, variance, and frequency content that do not change significantly across different time segments. Time domain methods like simply calculating the average amplitude or standard deviation across an entire recording work well here. However, non-stationary signals, which are common in real-world biological systems, exhibit statistical properties that shift with time, meaning the signal's characteristics are very different at the beginning versus the end of a recording. When you apply a time domain analysis method designed for stationary data to a non-stationary signal, you risk averaging out critical transient events or significant changes. The results might only reflect an overall average without revealing the crucial temporal dynamics. For instance, a simple Fourier transform, a common time domain technique, assumes stationarity over the analyzed window, and applying it to non-stationary data can lead to issues like spectral leakage, blurring the true frequency content. This limitation highlights why methods like time-frequency analysis, using techniques such as wavelets or short-term Fourier transforms, become indispensable. These approaches break the signal into smaller, overlapping windows, allowing for the analysis of frequency content as it evolves over time, providing a richer and more accurate representation of the underlying dynamics. Understanding these limitations is absolutely crucial for anyone working with biological signals, particularly in neuroscience. It is not just about avoiding errors, but about empowering researchers to unlock deeper insights into the brain's incredibly dynamic processes, moving beyond static averages to truly grasp the nuances of neural activity as it unfolds.